The Phantom Laboratory has produced this instructional video to illustrate the correct procedure for conducting a typical quality assurance test session. Commentary is provided by David Goodenough, Ph.D., a professor of radiology and co-director of the Institute for Medical Imaging and Image Analysis at the George Washington University, known for his pioneering work establishing test methods in evaluating CT scanner performance.
The Catphan really had its origins back in 1974. At that time, I had gone to George Washington University to undertake a research project on a new device that was called an EMI scanner, EMI being the first company that made CT scanners. Over the ensuing several years, we developed the concepts that are utilized in the Catphan, and those concepts led to some patents that were issued in 1977. Over the next 20 years, CT scanning changed remarkably. Scan times changed from minutes to seconds, and computer power, of course, changed accordingly. The net result was that the imaging aspects of CT scanners changed so dramatically that, luckily for us, we had designed the Catphan to be modular and upgradable, so we were able to adapt and modify the components to match the technology's change. After the year or two of research where we felt comfortable in establishing the basic methodologies of what was needed, we realized that we would have to work with an industrial partner, somebody who knew how to develop phantom-type materials, particularly formulate these new low-contrast plastics. So that's when we turned to working with the predecessor of the Phantom Lab in developing the original Catphan. And in fact, then, that is one of the challenges of the Catphan, as I mentioned earlier, in keeping up with technology. We've had to move from CAT scanners that resolve 2 millimeters to CAT scanners that resolve 1/4 of a millimeter. And this has been one of the aspects that we've been able to keep up with the modular design, so that we could replace a module that resolved 7 line pairs per centimeter with one that now resolves 20 or even 21 line pairs per centimeter. You could imagine over the last 20 years or more that we've developed many different modules and many different parts of modules. The Catphan is found around the world. As I look at tenders and bid specifications around the world, you'll find the Catphan specified. It's used by many regulatory and acquisition groups. More important, of course, to me is the fact that the scientific methods and concepts have been utilized and in many ways copied and found in scientific groups throughout the world.
Through our evolution of design and refinement, we now offer 3 primary Catphan models. The 412 and 424 are very similar, with the difference of the 424 has a liquid bath module and the 412 uses a solid cast uniformity module. The 500 was designed to address some of the key concerns which have been brought on by spiral CT.
One of the things that has changed over the years is that with the advent of spiral scanning, where the patient table is actually moved dynamically through the CT scanning beam, we actually have to encounter the situation of the modules being of greater thickness. The advantage of the thicker modules, particularly the 4 centimeter thickness, is that this enables you to monitor spiral scanning, where you may have objects from the slice above and the slice below essentially feed into the slice of interest. So if you consider a typical CT scan slice being 10 millimeters, you would need at least 30 millimeters. And so to make for some degree of tolerance, we actually designed the modules to be 4 centimeters in thickness.
In CT, the performance of the scanner is affected by a number of variables, and one of the most basic is the change in attenuation, which is brought on by the different sizes of patients or going from a head to a body. And to address these concerns and to be able to evaluate how the scanner's performance is in these different areas, we've developed a series of annuli which enable you to use different sized bodies or simulate the beam hardening effect of the skull and the head. Additionally, we've done research utilizing anthropomorphic shells and shapes, and that's something that is available to customers on a custom basis.
We are ready to begin a sample quality assurance test session. The Catphan Phantom case enables easy mounting and positioning. Cantilevering the Phantom off the end of the table eliminates potential table artifacts. The mount features adjustable bolts to level the Phantom. The Catphan Phantom is aligned using the marker dots on the Phantom and the scanner's alignment lights. To align the Phantom to the X position, slide the Phantom along the rim of the case. To align to the Y position, adjust the table height. To align the first test section with the Z-axis light, drive the table into the gantry. Once the Phantom is aligned, you're ready to scan. Test centers in the modules are spaced at specific intervals, allowing different test modules to be quickly scanned without repositioning the Catphan Phantom. Begin with a scan of the first section, CTP 401, at the 0 mm table position. The center of this test section can also be located on the scout view where the wire ramps cross. The 4 opposed ramps allow us to verify the Phantom position quickly. When properly aligned, the ramps should be centered in the image, as shown here. Here, we've deliberately offset the Phantom by 5 mm. Notice the ramps have shifted in a clockwise direction, indicating the Phantom is not aligned along the Z-axis. Verify the X and Y alignment by the Phantom's position in the center of the screen. The scanner's grid selection feature will assist you in viewing these axes. Incorrect alignment may indicate the need to recalibrate the alignment lights or the scout view accuracy. Test these by selecting and scanning the center of the slice section 1. Evaluate the alignment of the wire ramps in these images. After the Phantom alignment has been verified, select the appropriate module locations for your Catphan model and scan the remaining test modules. To measure the Phantom slice width, we establish the full width at half maximum of the slice width ramps. For this calculation, we use the region of interest measurement to determine the background CT number and subtract it from the peak CT number, where the ramps disappear with the smallest window setting. We then divide this number by 2 to get the mean and add it to the background. Set the level at the full width at half maximum number. Use the scanner's measurement tools to determine the length of the wire ramp. Because we use 23-degree ramps to increase accuracy, the measured wire length must be multiplied by 0.42.
The 23-degree angle is very nice because it gives us essentially a 2.5 to 1 magnification in the image plane, which makes the measurements of slice width much easier to make and much more accurate, particularly for thin slices.
The ramps can also be used to test couch incrementation accuracy by driving the table in and out of the gantry and testing to see if the Phantom is returned to the same position. The 4 thin rods in the center of the Phantom are used to measure linear distortion and pixel size. To test for distortion, measure the distance between the centers of the rods. Surrounding the ramps are 4 sensitometry or CT number samples. These are made from air, LDPE, acrylic, and Teflon. The samples allow you to monitor any possible CT measurement problems resulting from scanner drift. This evaluation of CT linearity is extremely important when evaluating CT scanners used for treatment planning. All Catphan models use a very dense tungsten carbide bead to create a point source signal for the modulation transfer function, or MTF, plot. This patented bead design eliminates the errors which can be caused by misaligned wires.
The reason we moved away from the thin wire as a point source to a small isolated bead was because a bead is much easier to align. We do not have artifacts from alignment such as streaking, and as such the small isolated bead constitutes a point source from which we can look at both the in-plane XY resolution and the z-axis resolution. In essence, we could look at the 3D point spread function.
In the 412 and 424 models, the bead is located by itself in a 25 mm thick test module. By obtaining a pixel list of the pixels surrounding the bead and subtracting the background value, the point spread function can be plotted. Here we see a computerized MTF curve derived from this pixel data. In the Catphan 500, the bead is cast with a visual high-resolution test in a 40 mm thick module, allowing greater z-axis scanning length for spiral CT.
The advantage of using the bead as a point source is that we can generate both the two-dimensional point spread function in the XY plane, or in fact the ellipsoid, the volume resolution, the 3D point spread function of a CAT scanner. In fact, when we take the profile along the z-axis, we are generating the slice sensitivity profile in the z-axis. We can alternatively generate this profile by stepping or moving the bead a small increment at a time, and by monitoring the peak CT numbers we can generate the slice sensitivity profile.
The high-resolution sections offer visual tests of resolution. In the 412 and 424 models, the high-resolution tests range from 5 to 11 line pair per centimeter on the upper side and from 12 to 20 line pair per centimeter on the lower side. The 500 model's test gauge ranges from 1 to 21 line pair per centimeter. In this test module, the gauge is set in a radial layout with a minimum use of material. This reduces artifacts which might distort the data created by the MTF bead, which is cast into the same section. The Catphan low-contrast sections use solid cast technology. The low-contrast test section in the 412 and 424 Catphan models test nominal low-contrast levels of 0.1%, 0.3%, 0.5%, and 1% for 8 targets ranging in diameter from 2 to 15 millimeters. This section can serve as a quick reference in comparative QA measurements. For example, on this system, we now see 6 targets at 0.3%. If the low contrast deteriorates, we may only see, for example, 3 to 4 targets. The contrast variation is the difference between the background CT number and the test target CT number. It is important to take several ROI measurements of both the test target and its surrounding area and average them to reduce errors caused by the image noise and uniformity variations. The Catphan 500 Phantom has a low-contrast section with both subslice and supraslice low-contrast test objects. The outer ring visible here represents the supraslice, the inner ring, the subslice. The supraslice test objects have the same 40 mm z-axis length as the test module. They have nominal low-contrast levels of 0.3%, 0.5%, and 1% for 9 targets ranging from 2 to 15 millimeters.
This presents some interesting challenges in trying to detect and visualize objects that are smaller than the slice width. For example, a 5 millimeter spherical tumor imaged in a 10 millimeter slice, only half of the slice width is occupied by the 5 millimeter tumor. And we call this an object subslice. It is thinner than the slice thickness. And again, this is an area that we've had to return to as spiral has developed and evolved, because this issue of sub-slice thickness object is very important in evaluating a spiral CT scanner.
In this spiral scan sequence, with 8 mm slices and an index of 1 mm, the subslice objects in the center intensify and disappear as the table moves the phantom. To test subslice low-contrast details, this test module includes truncated cylinders with 3, 5, and 7 mm lengths. These are cast from the same pouring of the material used in the 1% supraslice test object. The low-contrast section can be used to study how changes in data acquisition parameters can change the scanner's ability to identify subslice targets.
Interestingly enough, as you come to the midplane of the module, we run into the subslice objects, things that are thinner or less wide than the slice thickness. And you can see these objects will actually come and go in and out of the slice as the slice width sweeps through the subslice objects while maintaining the virtual resolution of the outer objects, which are the supraslice objects. It is not easy to predict what actually will be seen from a given spiral scan. There are many different variables that can be chosen, such as slice width and spiral interpolator and spiral pitch. And the prediction of what will be visualized is difficult. And so a phantom of this nature that provides both supraslice and subslice objects will really help the clinician in trying to understand the variables that influence detection and what they might hope to see.
Both the Catphan 412 and 500 use a solid cast, solid image uniformity module with a CT number within 2% of water. This tests the image uniformity and noise characteristics such as standard deviation. Closing the CT window, you may be able to visually identify non-uniformity problems, including rings, cupping, capping, and other artifacts. By selecting a profile which runs across the phantom, uniformity trends can be identified. To measure the image uniformity, use a constant ROI size, typically 2 to 4 centimeters in diameter. Measure the mean CT number in the center, 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock positions. Use the minimum and maximum CT numbers to calculate the image uniformity. Remember that on the Hounsfield scale, a deviation of 10 CT units represents a 1% variation. To measure the noise, select a constant ROI size from 2 to 4 centimeters in diameter and set your ROI cursor in the center of the image. Make your measurement using the scanner's noise standard deviation function. With some practice, a typical quality assurance procedure, such as we've seen here, can be performed in 15 to 30 minutes. Such tests are critical to verifying the integrity of a scanner.
The Catphan provides a test tool for monitoring your system performance. This monitoring will then be used to establish your own quality assurance standards, to provide a method to comply with regulatory groups, as well as providing a monitor of how well the system is being maintained, the service maintenance issue.
The quality assurance process can be automated using software purchased separately. The Institute for Radiological Image Sciences, Incorporated, or the IRIS Inc., has developed CT Auto QA for use on a standard PC. It allows images and data to be viewed, stored, printed, or transferred to database programs for time and trend analysis, including pixel size measurements from the 50 mm spaced rods. Here we see the phantom position. Slice thickness or slice sensitivity profiles, with their corresponding full width at half maximum. The CT linearity measurement, with the sensitometry material measured values. Note that the mean CT numbers for each material and the contrast scale are reported. The modulation transfer function derived from the point spread function, including the 50%, 10%, and the cutoff value of the MTF. The uniformity tests. The software automatically calculates the mean and standard deviation values. The vertical and horizontal profiles through the phantom center with measured fractional uniformity values. the low contrast resolution as predicted from the noise values. Auto QA is not provided with the Catphan Phantoms, but may be purchased from the Iris Inc. to automate these processes.
I get a lot of pleasure out of seeing the evolution of products, out of working with people and getting their ideas. We heard a lot of good ideas and observations from people in the field. We incorporated it into a design that enables the Phantom to be mounted off the case. We even have details like a level which is contained in the case. This kind of design evolution really is a result of both our internal efforts, but also our customers are bringing to us a great deal of useful and helpful information, and we look forward to that continuing challenge of meeting their needs as we move forward.
Although we're not sure where spiral CT scanning will go, the last 20 years has shown us that CT scanning is continuing to evolve and is a very exciting modality. Scanners may get faster. We can anticipate very soon now the era of multi-slice scanners where 2, 3, or more slices are being acquired simultaneously. One of the added advantages of the new thicker modules is that we will be able to monitor multiple slice CT scanners, and this will be a very valuable addition to the test tools for evaluating CT scanning. Well, if one considers that in the last 20 years we've gone through something like 4 or 5 generations of CT scanning, involving factors of 10 to or even 100-fold improvement in performance. It is remarkable that the Catphan has been able to not only keep up with that technology, but in many ways has led it. I think the test objects in the Catphan today are already at or beyond current levels of performance, but history shows that they'll probably catch up, and we'll have to develop new higher resolution test patterns and new lower low contrast test patterns, and so I don't really think that history has shown us anything else than that things continue to improve and get better.